Yeah, good afternoon all. Now I am going to explain about theoretical calculation on KVL and KCL. KVL is nothing but Kirchhoff's voltage law. Okay, the statement of KVL is algebraic sum of all voltages in a closed loop is equals to 0. See here in this loop, total voltages are V, V1, V2, V3, right? From this equation for minus plus minus V, plus minus plus V1, plus minus plus V2, plus minus plus V3 is equals to 0. Algebraic sum of all voltages in a closed loop is equals to 0. From that equation, V is equals to V1 plus V2 plus V3. Okay, we have to verify this value theoretically as well as practically. Okay, now we will see the theoretical calculations. Okay, let us consider three resistors. One is 1 kilo ohm, another one is 2.2 kilo ohm, another one is 3.3 kilo ohm. Okay, these three resistors are connected in series across a supply voltage of 10 volts. Right, because of this battery voltage, current I is flowing into the circuit, right? Okay, across passive elements, polarities will be plus minus and plus minus, right? Now see here, from the circuit, first of all I need to calculate total current I. Here three resistors are connected in series. I will get R equivalent value will be 1 kilo ohm plus 2.2 kilo ohm plus 3.3 kilo ohm, right? This is the R equivalent value here. Okay, then current I is equals to, from this circuit I can get current value will be I is equals to V by R equivalent, right? V value will be 10 volts, R equivalent value will be 1 kilo ohm plus 2.2 kilo ohm plus 3.3 kilo ohm, right? Then I will get current value as 1.53 milliamperes. Okay, calculation of current is over, right? Our aim is to satisfy V is equals to V1 plus V2 plus V3. V value is known, right? Next I need to calculate V1, V2, V3, right? V1 is nothing but current flowing through that branch into that branch resistance, that is nothing but V1 is equals to I into 1 kilo ohm, right? Similarly V2 is equals to I into 2.2 kilo ohm, V3 is equals to I into 3.3 kilo ohm, right? That is V1 is equals to 1.53 milliamperes into 1 kilo ohm value, you will get 1.53 volts. Similarly V2 is equals to 1.53 milliamperes into 2.2 kilo ohm, that value is 3.36 volts, right? V3 is equals to I into 3.3 kilo ohm, that is 1.53 milliamperes into 3.3 kilo ohm, right? That is 5.04. That means here V1 value is 1.53 volts, V2 value is 3.36 volts, V3 value is 5.04 volts, right? Then according to KVL, V is equals to V1 plus V2 plus V3, that is 10 volts is equals to 1.53 plus 3.76 plus 5.04, that is 9.93. 10 volts is approximately equals to 9.93, right? KVL is verified for 10 volts. Okay, similarly for 15 volts also. First we need to calculate current I, that is 15 volts divided by R equivalent value will be this one. Then we will get current value is 2.3 milliamperes, right? After that V1 is equals to I into 1 kilo ohm. Here I value will be 2.3, right? Then V1 is equals to 2.3 volts. V2 is equals to I into 2.2 kilo ohm, that is 5.06 volts. V3 is equals to I into 3.3 kilo ohm, that is equals to 7.59 volts, right? That is 15 is equals to 2.3 plus 5.06 plus 7.59, that is approximately equals to 14.95. 15 is equals to approximately is equals to 14.95, right? Hence KVL is verified. Similarly for 20 volts, first calculate current value. After that V1, V2, V3, you will get V1 value as 3.07 volts, V2 value as 6.75 volts and V3 value as 10.131 volts. Okay, now you can observe the tabular form here. For 10 volts, V1 value, V2 value, V3, that is 10 is equals to 1.53 plus 3.36 plus 5.04, approximately 9.9 something, verified, right? For 15 volts, these are the readings. For 20 volts, these are the readings, right? For different values of voltages, KVL is satisfied. Theoretically, these are the practical readings, right? Theoretically and practically. Okay, in this way we can do the experiment on, in this way we can calculate theoretical calculations. Now coming to KCL experiment, right? The statement of KCL is at a particular junction, the sum of incoming currents is equals to sum of outgoing currents, right? Now see here, this is the theoretical calculation circuit diagram. From this circuit diagram here I need to verify KCL, right? At this junction incoming current is I, right? outgoing currents are I1 and I2, right? That means here I need to satisfy total current I is equals to I1 plus I2. Okay, that means at a particular junction the sum of incoming currents is equals to sum of outgoing currents. That is the statement of KCL. Okay, now to calculate these currents, first by using equivalent resistance method, here from source side first I need to calculate equivalent resistance, right? Here I am calculating equivalent resistance, right? That means here 3.3 kilo ohm and 2.2 kilo ohm are connected in parallel, right? Here I need to calculate equivalent resistance on source side, then I have to proceed from opposite end, that is this side. Okay, here 2.2 kilo ohm and 3.3 kilo ohm are connected in parallel, right? Then the resultant value will be 1.32 kilo ohm, right? After that these two resistors are replaced by single resistor. This equivalent resistance will be connected in series with 1 kilo ohm. Then 1.32 kilo ohm plus 1 kilo ohm value will be 2.32 kilo ohm. That is, R equivalent value will be 2.32 kilo ohm, right? After calculating R equivalent value, calculate total current I, that is 10 volts divided by 2.32 kilo ohm. Then I will get current as 4.31 milliamperes, right? That means here total current calculation is completed. By knowing this total current, these two are connected in parallel. Okay, by using current division rule, I can calculate current flowing through parallel branch elements. That is, current flowing through 2.2 kilo ohm and current flowing through 3.3 kilo ohm. See here, current flowing through 2.2 kilo ohm value is I1 is equals to total current into opposite parallel branch resistance. That is, I1 is equals to I into 3.3 kilo ohm by 2.2 kilo ohm plus 3.3 kilo ohm. That is sum of parallel branch elements. That is, you can see here current I1 is equals to, right, current I1 is equals to total current value I into opposite parallel branch resistance, that is 3.3 kilo ohm, divided by sum of parallel branch elements. You will get 2.586, right? Similarly, current flowing through 3.3 kilo ohm resistor is nothing but I2, right? That is, I2 is equals to total current into opposite parallel branch resistance, that is 2.2 kilo ohm, right? 2.2 kilo ohm divided by 2.2 kilo ohm plus 3.3 kilo ohm, we will get 1.724 milliamperes, right? After that, total current I 4.31 is equals to I1 plus I2, that is 4.31. I equals to I1 plus I2 is satisfied. Hence, KCL is verified for 10 volts. Similarly, we can calculate for 15 volts. For 15 volts also equivalent resistance will be same. Then you after calculating this equivalent resistance, current I is equals to V by R equivalent, right? Then I value will be 6.465 milliamperes. After that, I1 value is I into opposite parallel branch resistance by sum of parallel branch elements. You will get I1 value is 3.879 milliamperes and I2 value is 3.586 milliamperes. Here 6.465 is equals to 3.879 plus 2.586, that is 6.465. KCL is verified for 15 volts also. Similarly for 20 volts, again just only voltage source value is changed here. R equivalent will be same, right? Why? Because there is no source effect on this equivalent resistance, right? Then current I equals to this V by R equivalent. We will get current value as 8.620 milliamperes. After that, I1 value will be 5.172 milliamperes by using current division rule. Similarly, I2 value is 3.448 milliamperes. Then 8.62 is equals to 8.62. Okay, after calculating those values, you can enter in the tabular form. Okay, for 10 volts, I1 value theoretically, I1 or I value. After that, I1, I2, right? I is equals to I1 plus I2 is satisfied. Similarly, for 15 volts also satisfied and 20 volts also satisfied. Okay, these are the practical readings. Okay, that is about theoretical calculations on KCL and KVL. Okay, thank you all.